Hello, everyone. So I'm going to talk about what happens mainly along the western Craton margin today. But first of all, just wanted to touch quickly about what a craton is. A craton is a very thick block of continental lithosphere that has survived from the Archean basically till today. And this is mainly due to the properties of their mantle keel, which is thick. It's buoyant, it's very light, so it can go into subduction. It's very dry and highly viscous, so resist also from rifting. And this explains why the cratons, Archean cratons, are still around today. And on the other hand, when we think about the craton margins, these are anticipated to have recorded multiple tectonic events, as these poor cratons are pushed around on the planet's surface in a plate tectonic environment, right? And so the idea, the flavor basically of the research of mine that I've been conducting in the last few years is try to test these concepts along the western margin of the Yilgarn Craton. So the Yilgarn, as many other, if not all Archean cratons that are preserved today, is wrapped by two Proterozoic orogens, one at the top, one in the north, and one in the south, that are at high angle from the main structural grain, Archean structural grain in the craton, which is roughly north-south. And then in the west, we have the Darling Fault, the Mesozoic Darling Fault, which is subparallel to that Archean structural grain. And so, yeah, the interest for me is explore, the evidence of the option that Archean fabrics might have had a huge control on post-Archean fabrics, or more broadly, try to understand how cratons, these very thick, stiff chunks of lithosphere, can influence plate tectonics in general, right? But today we are mainly discussing about the seismic data and their interpretation, and particularly with this talk, we're going to look for Proterozoic fabrics along the western margin. So do we have Proterozoic fabrics there as well, as we have in the north, in the south? Spoiler, yes, we do have. So the Darling Fault, it's a big feature. It's more than 1,000 kilometers along strike. Was active mainly during the Mesozoic, and Charmaine in the next talk will discuss that more in detail. Was active mainly during Gondwana breakup and associated with the development of the Perth Basin. But it's been known for a long time that flanking the Darling Fault, we have some ductile, quite wide belts with relatively high-grade rocks, amphibolite-facies rocks, high strain, and many names have been given to this belt: Darling Mobile Belt, Pinjarra Orogen, which is probably my favorite at this time, and the continuation of this belt in Antarctica has been named as Kunga Orogen. So high-strain fabrics, subparallel to the Darling Fault, that is north-south, steeply dipping, subvertical, possibly Archean or Proterozoic in age, or both. Yes, not a spoiler. Yes, we have both. So the mysterious Pinjarra Orogen, well, mysterious mainly because it's hidden. You can choose between hidden under a very thick package of sedimentary rocks, the Perth Basin, or the Antarctic ice. But it's mostly out of sight, but not out of mind, as there is a lot of interest both from the academic side in terms of we want to refine the models for the Gondwana assembly and Gondwana breakup subsequently. And also, as Fauna touched before, there is a lot of interest in terms of economic geology along the western margin of the Yilgarn Craton. So traditionally, the study on this Pinjarra Orogen in WA has been focused on those three main inliers that has been mentioned in the previous talks as well. And the good advantage of when you study this piece of crust is that you only have to deal with Proterozoic rocks. So the poor field geologist doesn't have to spend 50% of his time wondering if the structures that he is seeing in the field are Archean or Proterozoic. And this, believe me, it's a big advantage. The downside is that when compared to the size of an orogen, these inliers are tiny, they are very small. So there is a lot of question in terms of how we upscale the features that we see there. There's an upscaling problem. And so my question is, how representative are these inliers of the old Pinjarra Orogen, right? Which is much bigger than what these inliers are. On the other hand, one feature that has been traditionally overlooked is the ductile belt that we have exposed on the Darling scarp, so on the exposed footwall of the Darling fault. And there is a good reason to work on that. One, because it's never been studied systematically in modern times, and offers great exposure in terms of Yilgarn standards for almost 1,000 kilometers long strike, north to south. And well, the downside is that you're dealing with structures that are potentially in age vary between Archean and Cretaceous, and guess what? They're all parallel to each other, at least in terms of planar features. And so here the critical role of geochronology for fabric dating, on which I will touch a little bit more later. So how does the poor field geologist, how can the poor field geologist unravel and distinguish between Archean, Proterozoic, or even Mesozoic fabrics when they're all parallel to each other? And given that we don't have a great coverage of geochronology data along the western margin, well, one tool is to look at the late Archean granites. We spent a lot of time working in the core of the Yilgarn Craton, where there are Archean fabrics only. And late Archean granites, what team called the syncratonization granites, younger than 2650, mostly potassic granites, they're systematically underformed. I've never seen a pervasive regional scale shear fabrics in these granites. So when you find them with a pervasive fabric along the craton margins, as we do, there is a good chance that these are Proterozoic fabrics. The same applies to the mafic dikes, which range in age between the late Archean down to 1.2 in the craton. And in fact, when you approach the Darling fault, most of the dikes that are north-south striking, they are anticipated to be 1.2 in age, so the youngest suite that we find in Craton. And in fact, those that have been dated are in fact 1.2. So this is tectonic style, has been mentioned in the past as well in the previous talks. In the core of the Craton, in terms of Archean tectonics, we see a secular transition in tectonic style, dominant domain kill to transpressional orogenic shear zones, mainly along east dipping shear zones. So when we approach the Craton margins, if we see something that looks different in terms of geometry and kinematics, looks unusual in terms of Archean tectonics, well, the field geologist becomes suspicious. Of course, I wouldn't take this tool. I wouldn't use this tool as just alone, because we don't have a full inventory of Archean tectonic styles. But when we use it in conjunction to point 1 and 2, then it becomes quite useful as well. And of course, another important point again, direct fabric dating. So we have a PhD project which is just about to start, in fact, and we'll try to produce a lot of data directly in situ dating of the various fabrics along the Darling fault area, basically. So where we have actually found these fabrics along the Darling fault area by using basically those criteria that I've just listed. So well, in the north, in the southern part of the narrower terrain, we have some gently dipping southeast verging thrust that are probably we believe are related to the either Glenborg or Capricorn orogeny, or possibly with the components of both. And the biotite cooling ages that we have from that part of the world are consistent with that. Similarly, in the south, and this is the area between Nanap and Bridgetown, more or less, we have again shallow dipping fabrics, mainly striking east-west, that are most likely related to the Albany Fraser. And this is consistent also with the seismic lines, what the seismic lines further east in the Craton show. Raf showed some of those images before. And then focusing more on the north-south belt along the Darling Fault, with fieldwork, I've identified two main belts, one related to dextral, mainly dextral shearing in the southern part of the belt, the Waruna belt, and then in the north, the Chittering belt, which is mainly sinistral. And so based on this, this work, this data collection, my view is that we don't have any Proterozoic shear fabric preserved along the Craton margin, along lines 1 and 2, at least close to the surface. While the opposite is true in the southern line, where we have a variety of fabric ranging from, well, at least we have a number of Archean tectonic fabrics there, an unknown number, and then at least three generations of Proterozoic fabric, Albany Fraser, and then two related to the Darling Fault domain, right? Part of the Pinjarra Orogen. I just want to mention in between these north-south striking Proterozoic belts of the Pinjarra Orogen, we have this belt, which I have called Armadale belt, in which this belt is basically devoid of any Proterozoic overprint, so we have just Archean shear fabrics right there on the Darling Fault, basically. And this is not critical for this talk, but of course it's important in terms of the inheritance story, so how the Archean fabrics influence the development of the younger ones. And just to give an idea of the structural control that we have, or geological control in general, just from domain 4, so from Chittering downwards towards the southern coast, over the past few years, I've collected more than 1,100 structural sites, of some hundreds of thin sections, oriented samples, and so on, so structural data. So I believe we have a relatively good control of what's going on, at least at the surface. So just quickly about this Armadale domain, again, where we are right on the Darling Fault, and we have no Proterozoic fabrics, and it's been established based on by using the tools that I mentioned before. So we have late Archean shear fabrics developed in these 2680 granites and associated migmatites, which are older, and these are truncated by granites of the Darling Range batholiths, which are about 2650, and then by the Proterozoic dikes. And when you go away from this domain, so in the rest of the Darling Fault scarp, where we have the Proterozoic belt preserved, this is a nice aeromag image that really shows the different texture between the Archean domain at the right and the domain that has a pervasive Proterozoic overprint with this north-south striping area, which in this domain here we are around Waruna, is about 10 kilometers wide, but then of course the width of this belt varies, basically courtesy of the younger Darling Fault, of course, which have cuts through it. And so just a sketch from the field, what you see along this Proterozoic belt. You see Archean migmatites. There is also a metasedimentary component. And these are intruded by late Archean granites, in this case from the Darling Range batholith, so around 2650 or so. Then various Proterozoic dikes, most of which along the scarp are believed to be 1.2 GA in age. And then everything is sheared together under amphibolite facies conditions. This is around the P domain. When you go in the Archean domain, you basically have the same sequence of intrusions. You just don't have the bit at the top. You're just missing the amphibolite facies regional shearing event that you see at the margin. And the Chittering belt in the north is where the knowledge is a bit more advanced, because that's where I started working during COVID. And so we published this a couple of years ago. There is a lot of data, and This is available on our ebook store. It's a GSWA report. And so I won't spend much time on this belt. But just quickly, this chittering belt has a lot of migmatites, as we found a lot of migmatites all along the belt, but as a metasedimentary component, which is very useful because there's a lot of kyanite and sillimanite, so they offer strong metamorphic constraints. Here a beautiful example of synkinematic kyanite with the fine lineations and is incorporating the crystallized matrix there in these quartz-rich metasediments. Kyanite, which is in turn replaced along some retrograde shear zones by synkinematic sillimanite. So we are looking at decompression, we are looking at exhumation of this craton margin as a minimum of temperature over 500 degrees. This is just a quick overview on the preliminary geochronology data that we've been working on with Bruno and with Chris, and as I said, now with this PhD project starting, we have the aim of that is to improve this data set considerably and to provide more solid constraints. But just very quickly, so we have some 2.9 GA garnet edges that are possibly representative of some of the migmatitic events that occur in the Archean in this part of the world. And then we have some garnet edges and monazite edges there in blue, which are clustering around 750 MA, which are broadly overlapping with the timing of magmatism in the Lewin layer down south. And then we have a very good cluster of biotite edges, around 600 MA, which we believe represent the minimum age of the shearing that we see along the belt there. So these represent basically a timing where the whole belt cooled down to 350 degrees. And therefore the main sinistral shearing event that we see there along the belt probably developed between 650 and 700 MA. In the south, we don't have much data, but broadly the story is broadly consistent, except that we have another thermal pulse here in the south with zircon rims growing at around 620, followed by biotite edges, which at around 580, possibly suggesting some rapid cooling or exhumation. And then we have a distinctive younger group of biotite edges here, which broadly correspond to the the timing of metamorphic peak that we see there in the Lewin layer at around 520. And these are this metamorphic event is hot. We're looking at granulite facies rocks at around maybe 750, 800 degrees. And possibly these very young ages around 450s are flagging the onset of extension, the onset of basically Gondwana breakup in this part of the world. And on the bigger picture, this major sinistral event that we see recorded by the chittering belt fits well in the global reconstructions that where we see we need to accommodate about 3,000 to 5,000 kilometers of sinistral displacement between Australia and in India at about after 750 MA. So our data so far fit pretty well in this picture. So just very quickly, some metamorphic data. We only have one sample from the chittering belt, which plots there where that orange circle is. So we're looking at amphibolite facies rocks in the kyanite field. We have kyanite in our rocks, so that's fine. Then we see exhumation in the sillimanite field and down to greenish facies conditions, and this needs to be older than 650 MA. And these Proterozoic events are superimposed on Archean shearing and magmatic events, which include migmatization, possibly 2.9 and possibly some younger ones, and then intrusion of the late granites and late Archean granites and the various mafic dikes, and then at the end the Darling Fault event. So just a quick look at the various the bulk of the geometry and kinematics that we see here along the belt. I've just rotated the map, so north is on my left, and so I can show the map bigger. So we have this Armadale domain, which is Archean. So we have 2680 granite, MA granite, with a shearing event in amphibolite fish. These are very common age in the Archean. We have many translational shearing events at that time, so nothing new. There is a north-south subvertical foliation here. These are the poles to the foliation, the black dots, and the north plunging lineation there in red. Then we have the chittering belt here, which is associated with sinistral shearing, probably around 650, 700 MA, or in the Neoproterozoic, of course, truncated by the Darling Fault. And this chittering belt needs to be, we know, is younger than this Waruna belt, thanks to the overprinting relationships. And this Waruna belt, in which we find also the youngest dikes, the 1.2 dikes are sheared. So this Waruna belt needs to be younger than 1.2 GA in terms of the last increment of shearing. So one important point here is that we know that the Meso to Near-Archean migmatites and their associated north striking fabric was already in the present day north-south subvertical orientation by the end of the Archean. And therefore, these fabrics seem to have played an important role in controlling the orientation of the Proterozoic fabrics and then on the Phanerozoic ones related to the Darling Fault. So that's one important point. Another point is that in chittering we see mainly sinistral kinematics on a south plunging lineation. So there is a component of craton up movement, which I've sketched here. When we go down south in the other Proterozoic belt, the situation is basically mirrored. So we have dextral shearing on a north plunging lineation. But the thing that these two belts have in common is both of them reflect a component of craton up kinematics. They both oblique slip the bulk vector of movement, but there is a component of craton up. We'll see how this might be relevant when we get to the seismic interpretation. And this is what we see in the two lines MW1 and 2. We see the crust penetrating Darling Fault, which possibly offsets the mole a little bit. I believe along the margin of the craton, we only see Archean fabrics at the surface and probably also at depth. And overall, the Pinjarra crust, as has been mentioned also in the previous talks, is poorly reflective, but seems to be horizontally, mainly subhorizontally layered and possibly gently dipping to the east. When we move down south, and remember this is the corner where everything is happening, we have multiple Archean fabrics and then at least 3 generations of Proterozoic fabrics. In particular, we have the Albany Fraser fabric, which is basically as a strike that is parallel to the line, right? So it will be very hard to imagine to image here in these lines. So what we see here, again, the Darling Fault that goes down possibly to the base of the crust. And then overall, we see a crustal scale wedge. These, as Ralph mentioned before, are possibly Archean rocks, possibly with a component of Proterozoic rocks. But what is probably what I find very likely is that these rocks are part of the Pinjarra Orogen, as we see here at the surface, because this part we see has been is part of the chittering belt here at the surface. We are at the latitude of Nanap, basically, where the seismic line crossed the Darling Fault. So we have this ductile belt. And so this wedge here is probably, I would say, Archean Proterozoic rocks, modified, strongly deformed during the Albany Fraser Orogen, because you are just here along the main front, and then strongly deformed as well during the Pinjarra Orogen. What is important here, I guess, is that overall, as I mentioned before, both Proterozoic events associated with the Pinjarra Orogen have a component of craton up kinematics, which might be associated with this kind of under-thrusting component that we see here. So with this Proterozoic wedge basically stacked under the Yilgarn Craton. which is an interpretation that is consistent with craton up kinematics that we see at the surface, and also with the metamorphic data that, if you remember from the slide I showed before, there is evidence of exhumation of the craton margin in the Neoproterozoic, and also these east dipping shear zones, so which are obviously most likely have an important shear fabric in the Proterozoic, are subparallel to the east dipping architecture that Raf was showing before, which we know is Archean. So again, there is a possible story here related to the in terms of structural inheritance. So the dominantly east dipping architecture that is a craton-wide feature in the Archean possibly has been exploited and used in the Proterozoic during the Pinjarra Orogen. And I leave you with this.